A bit more about pressure and head, because I know these two terms can be a little bit confusing, and head, you use head for doing calculations of friction and static head, and adding that up for find out what kind of head you need to pump, and then there's pressure. And so how do these two actually relate? Well, let's go back to first video, where I'm just going to draw again a little schematic of a pump. No, maybe a little bit here. So we're pumping into another tank, and we had points 2, point S, point D, point 1. So we're pumping from 1 to 2. Usually the 2 is going to be a little bit higher than 1. And we have these 2 points that we're interested in, point S and D, and what we want to look at is the difference in pressure between these 2 points, because that's what the pump has to supply. It gets pressure from this side, but it's got to deliver pressure, so the difference is what the pump does. And we said that the difference in pressure at D, right, minus pressure at S, suction, over density, is going to be equal to the difference in height that we need to achieve. We need to get the water higher up. So that's H2 minus H1 plus the friction head, twin points 1 and 2. So this difference in height is known as the static head, and this is called the friction head. If we add these two together, we get the amount of head that the pump needs to provide. So I've just lumped this whole term together, made it disappear, and called it H for head, and that's known as the total head of the pump. So once I have these two numbers, I can go to a store, go on a graph of a pump, find out on the internet, whatever, and select a pump to do the job. So these two are very much related. So take a closer look. Pressure over, so pressure, we have difference in pressure. I'm just going to say pressure over density. Upside down is not so easy. Is equal to a height. I'm going to call it Z. Let's just change that up a little bit. So this is pressure, density, and height. Now for water, this turns in, and we need to get these, I want to get the units going properly. I want this to be in PSI, I want this to be in feet, and density will be in, say, in pounds per cubic feet. But so to get all these units working properly, what's going to happen, I'm going to find that P is going to be equal to 1 over 2.31 times Z. So Z divided by 2.31, Z is in feet, and P is in PSI. So we have a very neat relationship. We can use now a pressure gauge that measures in PSI, and we can measure heights in feet, and we'll have a very neat, easy correspondence. So how do we use this in practice? I looked up the definition of head in the Encyclopedia Britannica. Well, I don't have an Encyclopedia Britannica, but on the web, that's what it said. The definition was coming from the Encyclopedia Britannica. So, traditionally head was, I'm just going to draw what I think they meant by it in the dictionary, in the encyclopedia. It says that head is a body held in reserve at a height. So you have some sort of a reservoir at a height linked to some device lower down, and that's the definition of head. So typically, I suppose in those days, they might be thinking about water held in a reservoir that would lead to a turbine that would create electricity and or would produce power. So that's what head is the old definition was, and it works well for us, obviously, too. But we would call this now static head, and we'd take these two heights here, subtract them, and label that Z, for example, for static head. And if I wanted to know the pressure here, I could put a gauge, and the pressure would be equal to Z, the height that I measured, over 2.31. Or if I didn't have the height and I had the pressure, I could get the height, because the height might be difficult to measure. So, got a little experiment to show you concretely what happens with the term head or static head. Now, I've got a straw here. I'm going to pull up some water in this straw. There we go. Not so easy. I've colored the water red so you can see it a little bit. So I've got water, my straw, full of water. Now, how high do you think this straw could be? Like if I had a tube and I stood on the roof of my house, how high could it be to still hold this water here? Well, it's not difficult to figure out. We know we have pressure on this side of the straw. This is atmospheric pressure. Atmospheric pressure has been measured at typically around sea level, 14.7 psi. So if I wanted to know what height corresponded to 14.7 psi, I would take our formula, P equals Z over 2.31. So 14.7 times 2.31 is about 30. It's about 30 some feet. So this straw could actually be about 30 some feet high and still hold this water. Above that, you couldn't get it any higher. Now, there's you probably heard about the barometer reading. It's another interesting application for this little gizmo here. The barometer reading, a barometer is a tube like this filled with mercury. It's about 30 inches, 35 inches tall. So it sits like this in a reservoir of mercury. So we have pressure on top of the surface of the liquid, which would be mercury, and whatever height of mercury builds up in the glass will correspond to the pressure that's on the surface of the mercury. So if the pressure varies in the air, the pressure, the column fluid column height will vary. So I can use my formula again of P equals 2.31, Z over 2.31, but that's for water. So we know that mercury is about 14 times more dense than water. So the height that I'm going to get is going to be about 14 times less with mercury. So that's why if you figure it out, you'll see that you can get about 30 inches of mercury at 14.7 psi. So this glass tube will see a level of mercury about 30 inches from the surface here to the level of mercury in the glass. And that's the barometer reading. One last thing, I brought here also, I can create a syphon out of this little straw here. As you see, if I turn this over, I'm going to create a syphon because there's going to be low pressure at this point here, right? Because, I mean, the liquid is at high pressure down below, I mean, high atmospheric pressure, so as we go up into the straw, the pressure is going to drop. So if I let it go here, it's going to, it's going to go back down as you would in a syphon. So again, it's the story of how pressure varies inside a tube, and depending on, you know, if it's open, it'll you can figure out what the pressure is inside here, depending on where you're starting from, atmospheric pressure, and just using the height. So if you use again that formula, you would figure out that this pressure here would be the pressure equivalent to this height of water less than it is here, and that means low pressure here, therefore a syphon. So I hope this helped a little bit, and I think we've probably said enough about this for a while, and we can move on to other topics, and you're going to feel more comfortable about the relationship between pressure and head. Bye for now.
There is a sign in Munich that says, Heisenberg might have slept here.